Alright guys, so this is a video of just a simple example of, now we're getting into a little more complex trusses here. We've got this truss composed of these different triangles with joints at A, B, C, D, and E. And we've got a 100 Newton force acting downward on this truss. And this would kind of simulate, maybe you have a car in the middle of it, or an object in the middle of it that's applying 100 newtons of force sitting in the middle of the bridge. So what you can see is I've already established our pin and our roller in this particular case. And for this particular truss, we've got each member is 1 meter in length. So really basic dimensions and a basic force that's being applied to it. So let's go through the process of calculating the forces external and internal on this truss. So the first thing that I've given you here is step one is always calculating the external forces. And what I put on this diagram, we've got the force here at A in the X direction and the force at A in the Y direction, because that's our pin. Here's our other external force, reaction force, at the roller at D in the Y direction, and then here's our 100 Newton force. So we need to go through and calculate the external forces for this particular case. And first thing that we'll start with is we want to calculate, we want to look at the sum of the forces. Because this is in static equilibrium, we want to look at the sum of the forces in the X direction. We know that's going to be equal to 0 because it's in static equilibrium. So we've only got one force in the X direction. That's the force at A in the X direction. And because that's the only force and this thing's in static equilibrium, we know that that's equal to 0. Next thing we look at is the sum of the forces in the Y direction. We've got a couple different ones. We know, again, because it's in static equilibrium, that it's equal to 0, that the sum of those forces are going to be equal to 0. We've got the force at A in the Y. We've got this 100 Newton force coming downward, so minus 100. And we've got the force at D in the Y direction. And again, we know that the sum of those is going to equal 0. You can simplify a little bit. We've got two unknowns, so we'll have to come back to this one. So let's simplify this, move our 100 Newton force over, and we'll come back to that one. Last part, sum of the moments about joint A over here. That's where our pin is placed. So we're going to calculate the moments about that joint. Sum of the moments is going to take all these forces into account relative to their position to the 100 Newton force that's being applied to it. I'm sorry, relative to their position to the pin. So we've got the force at A in the X direction. We've got the force at A in the Y direction. And those are both at the pin, so they have a distance to the pin of 0. So those will end up dropping off. Our 100 Newton force is, we said all these members are 1 meter. So it's going to be minus the force times the distance from the pin. And then our last force is F dy, and that's going to be 1 and 2 meters away. So plus 2F dy. Those are all going to add up to 0. Drops off, drops off. The minus 100 we can move over, so we know that 2 times the force at D in the Y direction is equal to 100. And solving for the force at D in the Y direction, it'll be 50 newtons in this particular case. So there's our force at D in the Y direction. We can go over, plug this in, and subtract it, and we end up being able to solve for the force at A in the Y direction. That will also be 50 newtons. So just to step back for a second and think about what's going on. We've got a 100 Newton force acting downward, and it's directly in the middle, so it makes sense that the reaction forces at our pin and our roller are going to be equivalent. It's not shifted one way or another, therefore not applying more force in one direction or the other. Alright guys, so we've solved for all of the external forces on this truss. So our next job here is to calculate the angles. We said in the beginning that all of these members are going to be 1 meter in length. So that makes it kind of nice for us. All of these members are one length. That means we have equilateral triangles throughout this thing. So all of the angles in this particular truss are going to be 60 degrees. Just so you can see that this actually is the case, and to take you through the process if it wasn't the case, we would drop an altitude down right here. Let's draw a quick sketch over here of what's going on. Drop an altitude down. That means this is perpendicular. We're interested in finding this angle right here. If we chop this in half, that means this down here is 0.5. All the members are 1 meter. And so in order to solve for theta, we would take the cosine function. It relates the adjacent side relative to the angle to the hypotenuse. So we would get theta equals inverse cosine of 0.5 over 1, or just 0.5. And that would agree with what we said before, that this particular angle is going to be 60 degrees. You can do it with the other angles if you'd like, but all of them will end up being 60 degrees. Alright guys, so we've calculated all the angles, so the next part of this, in this process of solving this truss, is to go through kind of the lengthy process here of analyzing each of the joints. And so we want to do a free body diagram for each one. You can see I've written up here in this area what we've come up with so far. So let's start with joint A, and we'll model joint A with that free body diagram, account for all the forces that go into that particular joint, and then we'll go from there. Alright, so we've got FAX, FAY, we've got AB, and we've got AE. So let's go ahead and label all of those. So this is the force of AB. This is the force of AE. This is the force of AY, which we already know. This is the force of A, or at A in the X direction. And we also know that this is 60 degrees here. We'll get to that in a second. So we want to figure out the forces for all these internal members here. So we start with the sum of the forces in the X direction. Well, in this particular, in our free body diagram for this particular joint, we can see we've got 1, but we already know from up here, from previous, that that's 0. So we're not going to include that because we know the force on that is 0. We've got FAE in the positive direction. And we've got the X component of AB. So we know this is 60 degrees. We want the X component, so that's this guy right here. This is AB up here. So if we're going to write an expression for the X component, it's going to be AB times the cosine of 60. So let's plug that in. It's going to be plus AB times the cosine of 60. And those are all our forces in the X direction. We've got 2 unknowns here, so we're going to have to come back to this and substitute in a value, hopefully, that we find in the Y direction. Alright, some of the forces in the Y direction. We've got FAY, which we have a value for solved. That's an external force. We solve for that. That's 50 newtons. We've got the Y component of AB. So we need to come up with an expression for that. This is a 60-degree angle. That's the opposite compared to the adjacent. So that's the sine function. So the expression that we can come up with here is AB times the sine of 60. So that's going to be plus AB times the sine of 60. And those are all the forces in the y direction, so we can go through and solve. When we solve this, we're going to subtract 50 and then divide by the sine of 60. And that's going to give us our expression, or our force, of AB. Plug that into your calculator. Plug that into your calculator and you get AB, or the force of AB, is equal to a negative 57.74. Negative force, a little alarm bell should go off. That means that member is in compression. So take that, plug it back in up here. We end up with FAE plus a negative 57.74 cosine of 60 equals 0. Plug that expression into your calculator and move it over, and we'll get that the force on the member AE is equal to 28.87. So we solve for our two unknowns in that joint. We've got every member, the force on every member, and the external forces at that joint, so we'll move on to joint B. Alright guys, so we've solved for the forces at joint A. We want to move on to the forces at joint B. I've written up here just so we can reference what we figured out so far as forces go. When we look at joint B, here's my free body diagram. So we'll go ahead and go through this process. There's a little bit of something that we have to kind of take into account though. We'll get to that in a second. First thing we look at is the sum of the forces in the X. I know I've got the force of BC, and that's in the positive direction, so we'll write positive BC. Next thing we need to do is account for the X component of AB here, and we've got to be a little bit careful. If we stay consistent with the way that we've done it before, we know that this is 60. These are all equilateral triangles, so this is going to be 60 over here, and this is also going to be 60. But the way that we've done it before is we know that in order to figure out the direction of this vector, we need to wrap this thing all the way around until it hits our vector. Well, if we wrap around to a horizontal line, that's going to give us 180, and we need to add another 60 to it. So the angle that we're going to use here is actually a 240-degree angle. And if we do this, we can write our X component. This is the one that we're interested in right here. Sorry, it's getting a little jumbled there. This is AB, so we can write the X component as positive AB times the cosine is going to relate the adjacent to the hypotenuse of 240 in this case. So a little bit different there, something you got to pay attention to. What this allows us to do is always just stay consistent and write our diagonal components here and as positives, and then the cosine function will actually correct our sine if it needs corrected. So we've got that diagonal. We need to also do the same thing over here for this diagonal. Similar process. Here's my 60-degree angle. But again, I need to wrap all the way around until I hit my vector. And in doing so, if I wrap all the way around to this dotted line, that's 270, I need to add another 30 in order to get to this vector. So 270 and 30 is going to be 300. So when we write this X component, again, it's still the cosine function that relates it. This is BE, this vector down here. So this is actually going to be plus BE times the cosine of, what do we say, 270 and 30 is 300. And again, the cosine function will correct if it needs correcting as far as the positive or the negative for the x component of that of BE. So we know that all these are going to equal 0. Well, we go up here to what we figured out already, and we know AB is negative 57.74. We don't know BE yet, and we don't know BC. So let's simplify here. The force of BC plus BE times the cosine of 300 is going to be equal to, again, we said A was negative 57.74. So this is going to be a negative. We move it over to the other side, it becomes positive. And we could simplify this. We'll do that at the end though. So two unknowns. We need to go ahead and figure something out so that we can go back and plug in. So let's look at the sum of the forces in the y direction. Well, the only two forces in the y direction are these diagonals. So I'm going to go back up here. AB times the sine in this case of 240 is going to be the expression for the component in the y direction. Down here, we're trying to figure out this piece right here, an expression for that piece. So that's going to be BE times the sine of 300 was our angle that we're going to use in order to wrap all the way around to get to our vector. Well, we know what AB is. We can move that over. So BE times the sine of 300 is going to equal negative 57 sine of 240 becomes positive 57 if we move it over 0.74 times the sine of 240. Divide by sine of 300 on both sides, and we solve that, and we'll actually get a positive 57.74. So BE, we go up and kind of check out what we've learned here. We know AB is a negative, so that's under compression, but BE is going to be under tension because we got a positive for that particular member. Alright, so we have BE. We're going to go back up here and plug it in. And when we do, we end up with something that looks like this. Force of BC is going to be equal to this guy here minus 57.74, that's BE, times the cosine of 300. Solve for the force of BC by plugging that into your calculator, and you get a negative 57.74. So we got that guy, and we got that guy. Alright, next step here is to go ahead and analyze what's going on at joint E. You can see over here I've added what we figured out in the last step at joint B. So we've got everything that we solved for nice and neat and organized. That's a really good idea for you guys to do. Just keep everything organized. Alright, so let's go ahead and look at joint E, what's going on at joint E. Draw our free body diagram. So first thing is we've got this 100 Newton force acting down. We've got, what is that, EC going up and to the right. We've got BE going up and to the left. And then we've also got horizontal components here coming from each part. So let's go ahead and label. This is EC. Force at EC. This is the force at BE, which we know, so we'll use that. This is the force on ED. This is the force on AE, which we know, so we'll use that. And then this is the 100 Newton force acting downward. Alright, so let's go ahead and take a look at what's going on here and figure some stuff out. The force in the x direction is going to be equal to 0, the sum of the forces in the x direction. We've got a negative force at AE, and I'm just going to go ahead and plug this in because we've already solved for AE, so negative 28.87. We've got the force at ED, which is going in the positive direction. And then we've got the horizontal component of BE, but we already know what BE is. Alright, so what we have to be careful of is this in the positive or the negative? Well, we've already figured that out, so it's going to be a positive force and then we've got the horizontal component at EC. We know this is a 60-degree angle, so no special calculations needed here. I need this piece right here. This is EC. So that's going to end up being EC times the cosine of 60 degrees. All that's going to be equal to 0. We can simplify this a little bit by combining this guy and this guy. We don't know what ED is. Hopefully we'll figure that out. We don't know what EC is, so plus EC times the cosine of 60 is equal to, and if I plug that into my calculator, alright guys, so we're going to look at joint E now. I've added those other things that we figured out at joint B to my list of our knowns. So let's go ahead and analyze joint E. Some of the forces in the X, we've got negative FAE, and we know what that is. So we'll plug that in. FAE is 28.87, but in this case, we're looking at the force in the negative direction of that. So we'll have to negate it. We've also got the force of BE. And again, we've got to take into consideration what's going on. So this is BE. We need an expression for the X component of BE. We know that this is a 60-degree angle, but if we stay consistent with what we've done, we need to wrap around, and this will give us a 120-degree angle. So the expression for this particular thing is going to be BE times the cosine of 120. We can write that as a positive force. And that's going to correct, that trig function will correct that appropriately. The force of EC in the X direction. Another quick sketch. Again, this is EC. We know that this is a 60-degree angle here. So no need to correct it like we did up here. We need the force in the X direction. So that's going to be the cosine of 60 times EC. So we write that as plus EC cosine of 60. And then the last force that we need to account for is the force on ED. All those are going to add up to 0. Let's do some simplifying. We know what AE is. AE is 28.87. BE we know, it's 57.74. So when you combine these two, and I'll do the math in the background, but when you combine these two, we're looking at negative 28.87 plus BE is 57.74 times the cosine of 120. That's all going to simplify down to one constant. And then we don't know what EC is, and we don't know what ED is. So we can move this entire expression over. I'll let you plug that into your calculator. And we'll just go ahead and kind of skip around here, bring this down. My final expression is going to be EC cosine of 60 plus the force on ED is equal to, this thing simplified is negative 57.74, and we subtract that from both sides, or add that to both sides, and we end up with a positive 57.74 for this expression. Again, two unknowns, so let's go ahead and do the sum of our forces in the y direction. We should be able to get an explicit answer for one of the forces, and then we can plug back in. Some of the forces in the y. So we've got the force of BE in the y direction. Go back up here. That's this y component. So that's going to be relative to this angle. That's going to be the sine function. So it's going to be BE sine. And then again, we're going to write that as a positive and then use this angle wrapped around until we hit the vector. So it's going to be BE sine of 120. We need the y component for EC. That's this guy right here. No need for a special angle. That's our 60. We wrap it around and we hit at 60 degrees. So that's plus EC times the sine of 60. And then our last y component, or y force in the y direction that we need to account for, is this negative 100. And those are all going to add up to 0. Simplify. BE, we have solved for BE. BE up here is 57.74 times the sine of 120. Minus 100 plus EC times the sine of 60. EC times the sine of 160 minus 100 equals 0. And I'll let you go ahead and solve that. We're going to isolate EC, so we need to combine these two constants here and then divide by sine of 60. And when we do that, we end up with 57.7. And it's actually 3 when it rounds. But because these are all equilateral, we should have the same force. So I'm just going to write it as 57.74. So there's EC. We go back up and we plug it in into this equation. And I'll do it over here. a different color. Here's EC, here's EC. We end up with 57.74 times the cosine of 60 plus FED, the force at ED, is equal to 57.74. Again, we're going to solve this, so we're going to subtract this expression right here, which is just a constant from both sides. When we do that, we solve for the force at ED, and we end up with 28.87. All right, we're almost there. We're slowly but surely getting there. We've got EC is 57.74. Force at ED is 28.87. So I'll add this to the list, and then we'll move on to the next joint. All right, guys, finally, we're at actually our last joint. We haven't looked at C, but we've actually solved for all the forces at C. BC we found earlier was negative 57.74. EC we just found was 57.74. And then CD was, oh, that's the one we have to solve for on this last joint. And we also have ED down here. So we're almost done. Long process, almost done. So let's go ahead and draw our free body diagram at point, or at joint D. Here's FDY. Here's FDY. There's FED. And there's FCD. All right, we know that this is a 60-degree angle, but we'll get to that here in a second. We already know this one. We already know this one. The last thing to solve for is FCD. So let's go ahead and piece together what we know. It's in equilibrium, so the sum of the forces in the x direction are going to be 0. Well, what do we have in the x direction? We have FED. But over here, we already know FED is 28.87. The only thing we have to be careful of is this is pointing to the left. So let's go ahead and write that as a negative 28.87. And then we need the x component of FCD. So similar process to what we did before. This is our 60-degree angle. This is FCD. But again, we've got to wrap this around until we hit it, so the angle that we're going to use in our trig function is actually 120. We want the x component of this guy, so it's going to be cosine of 120 times FCD. So we're going to go plus FCD, or I sometimes just write it as CD, same thing there. And we want the cosine of 120. This trig function will correct, because this is actually going in the negative x direction, but the cosine of 120 is going to end up being negative. So that'll all work itself out. Move this over. CD is actually going to be equal to a positive 28.87 when we add to both sides. And then we got to divide by cosine of 120. So we plug that into our calculator, and we end up with CD is equal to negative 57.74. Again, a little alarm bell should go off. That's a negative force, so that thing is going to be under compression. That's the last thing that we need to solve for. So we're going to add this to our list, and I'll do that here on the next page, and then the last piece of this is we need to figure out what is under tension and what's under compression. All right, guys, so last piece of this, figuring out which ones are under tension and compression. These three guys are external forces, so we don't need to make that designation for those threes. We want to look specifically at all of the internal forces, or the forces on all of the members here and figure out which are under tension and which are under compression. So we've got the force of AB, which if you remember was this outer member right here. That's negative, so that is under compression. The force of AE is under tension, because it's a positive. Force of BC is under compression. Force of BE, tension. Force of EC, tension. Force of ED, tension. And force of CD is negative, so it's under compression. So we got AB, BC, CD, all under compression. Let's go back to our diagram and kind of look at what's going on here. So what we have here is our BC is going to be under compression, so that's the top piece. AB is going to be under compression, and CD is going to be under compression. All other members of this particular truss in here are actually going to be under tension. All right? Long video, long process, I know. Hopefully you've got the first couple parts solidified, and hopefully this was just more or less kind of review for you in solving the forces on the internal members.